Hopefully you've had a chance to try out these practice problems. If not, pause and give them a shot. I'm going to now walk through the solutions. And for all three of these molecules, we're being asked to draw its resonance structures and then calculate their formal charges. So I'm going to start with A. So I have to first start with a Lewis dot structure. So make sure you could build that Lewis dot structure. And there's a lot of different solutions for a lot of chemical formulas. And so choose one that has multiple bonds and lone pairs that could be rearranged to form something that with the same connectivity, but different electron distribution. So for this one, it's going to be, we've got a carbon that will, or I'll draw the Lewis structure for this one, and the others I'll do a little faster. All right, with my 4 valence electrons, and I have 3 oxygen atoms. So I'm going to place these around it. Okay, I'm creating single bonds. And I have a -2 charge, but I'm going to actually go ahead and take this electron on the carbon and make a double bond here. And then I can place my extra electrons at each of the remaining 2 oxygens. So that's going to give me something that looks like a carbon double bonded to an oxygen with 2 lone pairs. And then 2 oxygens will be singly bonded to the carbon with 3 lone pairs total. So there's an octet around the oxygen, there's an octet around the carbon. And it has an overall -2 charge. And that is me abbreviating a bracket. Okay, so now I have an initial structure. So to build my resonance structures, I'm going to rearrange this so the connectivity is the same. So what helps me is to go ahead and just build the same one with just all single bonds. And that forces me to keep the atoms arranged in the same way so I don't accidentally rearrange stuff and make a new molecule rather than a resonance structure. So once I have that, I'm going to say, I'm going to rearrange where that double bond is. Rather than placing it in the one on top, I'm going to put it over here. So if I do that, this oxygen with the double bond can only have 2 lone pairs and still obey the octet rule. And the 2 with the single bond really need 3 lone pairs. So I'll put my 3 lone pairs there, and I'll see that I have essentially the exact same molecule. It looks like I just went and like rotated it, but I've really shifted where that double bond is and replaced it with lone pairs. Now, the organic chemist in me wants to show you how to shuffle electrons around using arrows. So I'm just going to do that for my own enjoyment. What I'm really doing here is I'm taking a pair of electrons in my lone pair and building a double bond between a carbon and oxygen. I'll do this for the next one. And then that double bond here, one of them to the oxygen, if I just create a new double bond, I'll have 10 electrons to carbon. That won't work. Well, one of them comes up here and creates a new lone pair on the top. And so I've essentially shifted electrons into a bond and shifted them out of a bond up into a lone pair. And this is the kind of electron shuffling we do in organic chemistry. And so if I do that, right, I'll be able to create a third structure. It's going to look like this. So the one I just kind of showed how the electrons are going to move around. So starting with my single bonds, my like template, it's having that double bond here, leaving only 2 lone pairs on that oxygen with a double bond and creating a third lone pair on the one that now has only a single bond up at the top. And we still have this one untouched to the left, and it has, these all have a -2 charge. I have 3 resonance structures. Now we typically show these with brackets. And to show that they're equivalent, we put this double arrow in between them. So here's kind of the classic way to show resonance structures. There you go. I have 3 resonance structures for CO3, -2. And these are polyatomic ions. Okay, so now let's look at the formal charges for these. I'm going to switch colors. So for my formal charges, since these are resonance structures, they're going to be very similar. So I'll go in detail on one of them and then just put them for the other 2. Let's do this one in the bottom right. So for my carbon, I am going to have 4 valence electrons minus the sum of the number of non-bonding electrons, which no lone pairs, so 0, plus then the number, or I'm also subtracting the number of bonding electrons. So I've got 4 bonds to the carbon. So that's 8 electrons participating in a bond, 1/2 of 8. So that's going to equal 0. So carbon has a formal charge of 0. I personally like to write them next to it just to kind of help me like look at it all at once and see the formal charges right by the atom, but you don't have to. All right, let's do this oxygen right here. It has 6 valence electrons. And I'm going to do this a little bit different for each one just to kind of show the different ways to kind of format it that might work for you. So I have 6 valence electrons. I'm going to subtract the number of electrons that are in lone pairs, and that's 6. And then I'm going to subtract the number of bonds, or 1/2 of the bonding electrons. So there's 1 bond, so I'll do minus 1/2 of 2 electrons that are bonding. And that's going to give me -1. So I've got a -1 on this one. So on this oxygen right here, I've got 6 valence electrons minus my 4 non-bonding or lone pair electrons, and then minus 2 bonds. And see, I did that differently. I could do minus 1/2 of 4 bonding electrons, or I could think of it as minus 2 bonds. Oh, you can't see that. Sorry. So that's going to give me a formal charge of 0. So a 0 on this one. Last one right here. So this one's really similar to the one we did previously. So it has 6 valence electrons minus the 6 electrons that are non-bonding, and then also minus or plus within the sum of the parentheses, the 1/2 of the 2 electrons that are participating in a bond. So that's going to give me a value of -1. All right, so double check here. My formal charges are 0 plus 0 plus -1 plus -1. That gives me a total of -2. That matches my overall charge. So that's important to make sure we do. So I can see that I only have formal charges on the 2 oxygens where I added those extra electrons actually. So now going through my other 2, I'll see something similar. So I'm just going to put them down. I'll have 0 formal charges on my oxygen and the carbon and the oxygen with 2 bonds and 2 lone pairs, and a -1 formal charge on my oxygens that have 1 bond and 3 lone pairs. Oh, sorry, this one I have all my writing on. It had the double bond here. Okay. So that's evaluating the formal charges for my different resonance structures. Let's do the other 2. We'll do them a little bit faster. Sorry. This keeps defaulting to draw with my finger instead of move the page with my finger. So just to get a little more space, I've added a second page here. Okay, so let's do number B, C6H6. So there's a lot of ways you can draw this, but only one where you're going to get resonance structures. And it's when it's in a ring, 6-membered carbon ring, which I enjoy. And they have alternating double bonds, and they're each bonded to 1 hydrogen. And the interesting thing about this structure is that it has no lone pairs to work with, just double bonds. And this is what we actually call a conjugated double bond system. And they're special. And that they'll have resonance structures. And so in this case, what we can imagine doing for a resonance structure, sorry, let me switch colors, is moving all my double bonds over to where there's a single bond. And what this would create is a structure that looks the same, except the double bonds and single bonds have switched. But each carbon is still bonded to 2 carbon and 1 hydrogen. Each carbon has a double bond and 2 single bonds to it. So it's equivalent electronically. It's just delocalized those electrons that are participating in the second bond. We could put brackets on these. All right, so now if we want to calculate the formal charge, what we would do is we could come in here and let me switch colors. So for this carbon right here, we have we have valence electrons of 4. and we have 0 non-bonding electrons, and we have 4 bonds. And so we're going to get a total of 0 formal charge. For this hydrogen, we have 1 valence electron. We have no lone pairs, and we have 1/2 of 2 electrons participating in the bond. See, I did this the 2 different ways. So this is also 0. And so there's nothing different between the carbons and hydrogens here. And you can go ahead and try to calculate the formal charge slowly for each of them. But you'll find that all of these carbons and hydrogens have a formal charge of 0, which is ideal. Ideally, everything in our molecule has a formal charge of 0, especially when we have a neutral molecule like this one that shouldn't have overall charge to it. All right, let's do our last one, NCO. So here I'm going to put my carbon in the middle and a triple bond to my nitrogen and a single bond to my oxygen. Now I have an extra electron, which is good because I'm going to need to add one here to this oxygen, right? My carbon has no lone pairs, but my nitrogen will have 1. So here's one of my resonance structures. And I can imagine building another one where I move one of these one of these multiple bonds over to the oxygen and maybe one of these electrons over to the nitrogen. And you can think of them flipping, or you could think of kind of like this, or you could imagine this as a chain reaction where these electrons become the double bond, which kicks one of these bonds into a lone pair on the nitrogen. I prefer the second way to visualize it personally, but whatever gets you to a resonance structure. All right, so let's build another one. So here I'm going to have 2 lone pairs on my nitrogen, double bonded to my carbon, and double bonded to my oxygen. I can do a third. What if I had nitrogen as a single bond with 3 lone pairs to my carbon, triple bonded to my oxygen with just 1 lone pair? So here are my 3 resonance structures. Let's evaluate their formal charges because not all of these are going to contribute as much to our hybrid structure. So in our first one, let me switch. Our carbon is going to have, here we go, 4 valence electrons minus 0 bonding or non-bonding electrons minus 1/2 of 8 bonding electrons. So that's going to equal 0. So it's going to have a formal charge of 0. Our oxygen here is going to have 6 valence electrons minus 6 that are in lone pairs minus 1/2 of my 2 bonding electrons for a formal charge of -1. My nitrogen has 5 valence electrons minus its 2 electrons that are not bonding and in a lone pair minus 1/2 of the 6 valence electrons that are participating in the 3 triple bonds. So that's going to give me an overall charge of 0. Right. So now if I go through and figure out the formal charges on my other resonance structures, I'm going to see that my carbon stays at a 0 formal charge. Now in the middle one, my oxygen has a 0 formal charge, and my nitrogen will have the -1 formal charge. In my last one, carbon will be 0, nitrogen will be -2, and my oxygen will be +1. So our formal charges are really different here. Now we can actually evaluate these and say which one is best. And that one that's best, which means it minimizes its formal charge, will be the one that contributes the most to the actual structure of this molecule in nature, or it contributes the most to the hybrid structure. Maybe it's the way to think about it. All of these, though, show that there's a delocalization that's possible of the electrons across the bonds between nitrogen, carbon, and oxygen. So remember our rules for thinking about formal charges. One, you want to minimize the number of formal charges that you have, like the magnitude. And so that automatically makes these first 2 structures more favorable than the last because of that -2 charge and +1 charge. That's just more formal charge than the other 2 structures that only have 0s and -1. Okay, but looking at this, remember the next piece of it. The negative formal charge is on the most electronegative element. So the element that has a highest electronegativity of these 3 is oxygen at 3.5. Nitrogen's 3.0, carbon is 2.5. So I can write that down. So so carbon's electronegativity is 2.5, nitrogen's is 3.0, oxygen's is 3.5. So the oxygen is most likely to have the negative charge. And so that means this one right here, where the formal charge of -1 is on the oxygen, this is our most reasonable structure. So this one is the most reasonable. You could think of it as contributing the most too. This also shows how you would evaluate multiple possibilities for Lewis structures for a chemical formula. You can go through and assign formal charges, and whichever one minimizes the formal charges and puts the negative formal charges on your most electronegative element is your most reasonable Lewis dot structure.